Good morning, everyone. Welcome to our webinar, which is about the computable general equilibrium model and related with the OSAM project. So we welcome you all, and in particular, we welcome the project coordinator, Andrea Castelletti, which will introduce you with few words about the OSAM project, and then we will give the word to our speaker, Ruslana Palatnik, Professor Ruslana Palatnik from Israel College in Israel. So, Andrea, if you are connected, you may.
Yes. Good morning, everyone. Yes, I'm trying to figure out. Okay, you should see me too. Yes.
Yes.
So I just want to make a very short introduction to the project, assuming that most of you know already the project. OSAM is a primer project organized over 3 modeling layers. The idea is to explore interdependencies between water, energy, food, and ecosystem, mostly along the River Nile and that part of Egypt. And the idea is to, say, design some portfolios, which are planning options, which are then evaluated across these 3 scales, which goes from a micro scale, where we have a demonstration site, where we are exploring aquaponics, which is the combination of hydroponics and aquaculture, and try to infer and retrieve from these experimental experience some parameters, some information to be used at the mesoscale level, which is where we are looking. Elena, please, next slide. Exactly, where we're looking at the whole River Nile Valley water infrastructure system, and so how these dams and diversion dams are operated. We use the information from the micro level to say reshape potential future demand, assuming that because of population growth, because of climate change, this water demand may change, and so hydroponics may be an interesting complement to existing surface water supply system. And then we have the macro level, which is the topic of today talk, which is what happened outside the river basin, at the regional and continental and global scale, and how policies at that global scale can influence the lower level scales. So Ruslana today has kindly accepted the invitation to give us an overview of the models, the macro level scale, which is a computable global equilibrium model. And so I guess that's enough as an introductory say speech. So maybe we can give the floor to Ruslana to get more information about this.
Yeah, I will go to my screen. Do you see it now? Do you see my screen?
Yeah, we see.
Thanks. Perfect. So hello everyone, and thank you for the opportunity to present the models that we employ in the Israeli team for WOPEC3, together with Dr. Yuda Sirota from Israel Valley College and Orna Raviv and Mordechai Schechter from University of Haifa. So I was asked to give a bit of a detailed representation of the model. So I will start with the basic concept of the computable general equilibrium, and then I will discuss a bit of strengths and the limitations of the model and the challenges and also advantages of collaboration between this top-down model with the bottom-up models that you guys employ. And I hope that we will have some time to discuss the potential collaboration. Okay, so just a bit about myself. I am a senior lecturer at the Department of Economics in the Israel Valley College, In my PhD thesis, I developed a computable general equilibrium model for the Israeli economy to evaluate the economy-wide impact of carbon tax. This was back in 2007. I must say that in the last few years, I have been a part of the research team that served as a basis for carbon tax that was actually revised as a part of the next year budget in Israel. In addition, for my postdoc, I spent a great year in Venice. I joined Fondazione Enrico Mattei in 2007 in the climate change modeling and policy program, where I was working together with Francesco Bosello and his team on developing the GTAP-based modeling framework for climate change impact analysis, focusing on the agriculture and land and water management. Since then, I am working on different parts of climate analysis using the CGE. Here in this paper, I just wanted to show a few selected publications on this topic. In this paper, we analyze the economy-wide potential for Israel to meet Kyoto targets. Then, together with partners from Finland, we analyze the integration of general and partial equilibrium in agricultural land use transformation for the analysis of climate change in the Mediterranean. Together with Roberto Rosson, we published a paper on the more technical part of the integration between top-down and bottom-up models that I will discuss later on in this lecture. And here we have a few papers that were focusing on alternative water types using desalination and treated water as a part of the solution or adaptation policies to for Israeli mitigation or adaptation to climate change. Okay, so what are we talking about? What is this CGE? So C stands for computable, meaning it is solved numerically. G stands for general, meaning economy-wide. And equilibrium, meaning that there are optimizing agents that have found their best solution subject to their budget constraints. As we will see later, all the quantities demanded should be equal in the equilibrium to quantity supplied in both factor and commodity markets. And there should be an economy-wide macroeconomic balance. So a few words about the importance of the economic policy modeling and simulations. Unlike most of physical scientists who can test the ideas on controlled experiments in laboratories, economists have to rely primarily on natural experiments for their data. But the rapid development of modern computer and IT provides a means for today's economists to examine their ideas by computer-based simulations, models, before they put into practice. So simulation and economic modeling has become a major field in applied economics. Why this specific type of models are so popular? First, because they are theoretically consistent with the economic theory. They have, from the very beginning, a clear policy orientation. The unique feature, which is also relevant for our discussion here, is that CGEs capture both direct and indirect, intersectoral, interregional, intertemporal effects induced by policy or other types of changes. These models are able to provide more concrete welfare analysis that influence real policy making. they are able to analyze large, discrete changes that are far away from the baseline. And this is important. Minor changes are overshot in these models, but some large economic impacts are definitely well analyzed by these models, as we will see. These models are very useful to build a bridge between economists, stakeholders, and policymakers, and provide them with a base for dialogue. Now, some applications of the CGE methodology. Originally, it started from analyzing the impact of tax report and specifically trade liberalization, such as WTO negotiations in the 80s and 90s. Then they were applied to economic integration and analyzing the changes in world prices, to analyze the economic growth in the dynamic modeling framework, analyze how changes in public expenditure will impact the welfare. And in recent few decades or so, they are widely employed for energy and environmental policy analysis and climate change impact, as well as adaptation and mitigation policies, which is also what I am focusing in my modeling work. So some basic concepts. What is the CGE model? The basic components of the CGE models are, first of all, set of economic agents with the behavioral rules. Yeah? When we say agents in the economy, we mean firms, like factories and companies that attempt to maximize profits and minimize costs, and households who are assumed to maximize welfare consumption by choosing the consumption of goods and services according to their prices. Another set are the markets, where prices adjust until the supply and demand are equal. So the main strengths of the CGE is a combination of the standard theory and very detailed data. I will develop on both of these issues. The optimization and micro foundations are in the basis of the model. We are starting from improvement from the Keynesian macroeconomic models, where households respond to changes in prices, firms change their outputs and inputs when markets shift. And this type of analysis provides the evidence to support claims. Like benefits and costs can be calculated and used as evidence to support particular policies. We also can identify and qualify trade-offs between different policies. Okay, so now just graphically illustrate what is the difference between partial equilibrium and general equilibrium model. I remember that most of you are non-economists, so I will do my best to speak in a general language with just a few basic economical principles that I will present, okay? In order for you to feel what the model is about. So, if we analyze the basic representation of a market, let's say market for rice, we have a quantity of rice on the x-axis and the price on the y-axis, right? The demand for rice declines, and as prices increase, and the supply is assumed to increase with the price. The initial equilibrium is set where the demand meets supply. Here, the prices and quantities of how much rice is sold in the market is defined in the initial equilibrium. Now, assume that for some reason, it doesn't matter what now, maybe because of the decline in precipitations, and the need to irrigate, the supply of each unit of rice becomes costlier, okay? And this is described by the shift in the supply curve leftward. Now the demand meets supply at a higher price of rice, and a lower quantity of rice is sold, okay? This is very basic economics. In this analysis, we ignore possible impacts of the new equilibrium price and quantity of rice on other markets. And this is why this type of analysis is called partial equilibrium. Okay? It's a very important type of analysis, but this analysis is focused on a single market. This is why it is partial equilibrium. Okay? Now, in general equilibrium, we consider the interaction between different markets explicitly. What does it mean? Okay, let's take, for example, a market for water in Israel or California or other regions where the water is priced per unit. Okay, if the cost of supplying water increases due to droughts or investment in new costly infrastructure, so this may be the reason for a decline in the supply in rice that we analyzed before, and maybe also in the supply of electricity, if the electricity is at least partially generated by hydropower. Okay? Now pay attention that the links go both directions. For instance, water sector is very energy intensive. This means that rising prices of electricity can in turn impact the costs of water, okay? And we can continue in these interlinks to many other markets, including the labor market. In addition, for instance, for the reason of shortage in one of the reasons for the shortage in semiconductors that we experience around the world are rooted in the drought in Taiwan. Did you know it? That Taiwan supplies half of the semiconductors in the world market. Apparently, production of semiconductors, I learned, is very water intensive, and the 2 years drought in Taiwan increased the cost of production of semiconductors and reduced the production, the quantities that is supplied. So as we see in this example, the shock to the local market in Taiwan has implications to the global economy, okay, through the international trade of this important part required in every electronic appliance. So in CGE analysis, we talk about the baseline data set, the structure of the model, and then once we have the initial calibrated equilibrium, we imply shocks and receive new results, and then we do some kind of comparative static analysis to analyze the new equilibrium comparing to the previous one. Is it better off? Is it worse off? To different agents of the economy. Okay? So how we see this in our representation, I go back to the previous slide again, and let's see what we have in terms of general equilibrium model. So the initial equilibrium in each of the markets is collected in the actual baseline data, which I will describe in more detail later. But those quantities and prices, okay, come from statistics, from actual national accounts of the value sold in each of the markets in a given year. Okay, so this is monetary value which is price times quantity in each of the markets. Now, the theoretical model basically reflects the demand and supply functions of each of the markets, and also the links between the markets through what we call or usually use nested constant elasticity of substitution functions. I will explain it a bit in a few minutes. Then so this is base data plus functions from the model, okay? And in the initial equilibrium is calibrated. Then we impose an exogenous external shock, such as drought or tax or any other kind of shock, and the model calculates the new equilibrium that is reached simultaneously in all the markets, okay? Simultaneously because they all react and respond to the changes each in another. Okay. Now, a bit about this functional structure that I mentioned already. So the technology, of each sector, each product, each industry is specified with smooth neoclassical production functions, usually constant elasticity of substitution, the CS, usually nested CS, which yield a complete host function where all inputs are included. This is called the deep structural function because the technology and motivation, which is a profit maximization, and the signals to changes, mainly caused by prices change, are specified. And from here, we can determine the equilibrium prices and also returns to the factors of production, such as wages for labor and rates for capital. So just to give you a flavor, what is this elasticity of substitution and how does it work? I will give an example of what we have done on estimating the elasticities of substitution between different water types. Okay, here let's define sigma constant elasticity of substitution between water types, and by water types I mean natural water, treated water, and desalination. And sigma stands for the substitution between the water types in agricultural production. Okay, it basically is reflecting how easy to substitute from one type to another when the relative prices of water types are changing. Okay, so we assume firms' behavior in the neoclassical model with cost minimization objective. Then the CES production function of agricultural output Q is represented in this general form of CES function, where alpha is distribution parameter, W1 is quality of water type 1, W2 is quality of water type 2, and sigma, as I said, is the elasticity of substitution between any two types of water. So in the standard reduced form of the first order conditions, we see basically that if, for instance, price of water type 1, PW1, increases, the price of even if the price of water type 2 didn't change, it becomes relatively cheaper to use water type 2 because water type 1 became more expensive, right? So the question is how the producer, in this case, the agricultural production firm, how will he respond to this change in relative prices? Is he able or is she able to use the water type that is cheaper? This is what the elasticity sigma stands for, okay? We expect that if water types are substitutable, if it is possible in general to substitute between natural waters and desalinated water, then sigma should be positive, okay? Because if the price of natural water increases, we switch to the other type, desalination, and the other way around, okay? Now, if sigma is close to 0, then the substitution between water types is nearly fixed or unresponsive to the changes in relative prices. If, on the other hand, sigma increases, the higher sigma, the easier it is to substitute from one water type to another. Okay? So this is something that we did in the paper with Zvi, where we estimated the elasticity of substitution between different water types for Israeli water sector in Israel general. But this is just to give you an example how the elasticities work and why this is an important parameter in the functions behind the CGE models. Now, the CGE has a descriptive equilibrium. Okay, what does it mean? We use the equilibrium concepts, which greatly simplify model specification and often also the solution. Okay? It enhances the model clarity and transparency because model behavior consistent, as I said, with the economic theory. And it facilitates the validation of kind of predictable empirical results from the shocks. Now, the CGE model reflects a closed circular flow of production, income, and demand. We already saw the link between markets. Here in this diagram, I want to stress that the model also links the markets with households and supply of labor. The households that supply labor, they also receive income and pay taxes to the government. A part of direct consumption, the households and government save and invest in domestic and international capital markets. In addition to goods and services produced in the economy can be traded either domestically or exported. And in parallel, the important goods and services are traded in the market. We have also the macroeconomic closure. To summarize, the global computable general equilibrium model simulate the interaction of national economies across world markets. Okay, so we can have a general equilibrium for a single country and or for the entire world, the economy of the entire world. So here we determine national and also world market prices. Okay, CGE models are complete in the sense that they incorporate all economic activity in the economies that are simulated. We have the production, meaning the supply, the income to agents, meaning the wage for labor, the income from taxes to government, and the capital to enterprises and the rents they receive. We have the representation of the final demand, consumption, investment, and government purchases. We have the exports and imports, prices and wages and land rents, and also exchange rate in the international markets. All the markets are clear, meaning that supply meets demand in each and every market. And from here, we determine the prices in each of the markets. And also wages and profits and land rents are determined in the same simultaneous equilibrium. And the final remark on the modeling structure is that the CGE model is closed in the sense that these models account for all economic activity. There is nothing left outside. All the economy is represented, no leakages. Okay, so now if we got a sense of the model, let's talk a bit about data. So for baseline data, we need two sets. One is coming from the social accounting metrics, SAM, which is the accounting framework that describes the economic universe of the models. It experiences the rule of double entry for bookkeeping, meaning that expenditure receipt accounts of all economic agents must balance. Okay. And another set of data should be those elasticities, elasticity of substitution between different water types that I presented before. These are the key parameters that measure the responsiveness of economic agents to the price changes. These are parameters that we can impose or estimate for the model to work, to replicate the data. Now, we use GTAP database, which is very useful when the analysis is beyond one single country. In this database, I present you version 9. In the meantime, version 10 is also published. You can see they have about 57 sectors, 57 economic industries that are explicitly represented. Now, here you have the snapshot of the SAM. 1 second. The activities and commodities here are the sectors from the previous table. Okay, so in each row and column of activities and commodities, you have 57. You should divide them by 57. Okay, and now each column of activities represents how much each sector bought intermediate inputs from other sectors and itself. Factors here reflect how much was paid to labor, capital, and natural resources, which are also primary factors of production. The summary of each column, sum of each column of activities, is therefore the total actual expenditure of each sector to other sectors and so on. I remind you that here we have the actual monetary values from the official statistics. Okay. Now, in the second column of commodities, you see the reflection of supply of each sector, in addition with taxes paid by the sector and imports, we have overall supply of the economy for a given year. Considering the time, I will not go over each column and row, but I want to draw your attention also to the second row here. Each row in this matrix shows how much each sector sold to others, okay? So columns is how much we bought and rows is how much we sold, okay? Here we have the goods and services sold to other sectors, which comprise the overall intermediate demand. Then we have also what was sold to households, to government, or exported or sold as investment. And the overall sum of this row reflects the demand by the users. Now, each row in the matrix must equal the total of each row in the matrix must equal to the total of the corresponding column. Okay, so here we see the reflection of supply that equals demand in the baseline data for each and every sector in the economy. Now, in the global model, the data we saw in the previous slide is provided for the regions for all the regions in the world according to this disaggregation. In the GTAP 9 version, we have 123 regions. In this map, you can see the regions for which the data is available. Gray and green countries are represented specifically in GTAP database. White regions mean there is no separate data for those countries, and they appear only within the aggregated bundle with other countries of the region. So even though the data is available for most of the world in GTAP, the data for most of the countries of North Africa is available only on the aggregated level. So all those countries together, not separately. Now that we have a basic idea of the model and the data, let's discuss the shocks. By shocks, I mean alternative scenarios that can reflect vast variety, okay? Like impact of climate change on agricultural productivity, or capital loss due to sea level rise, or energy consumption that may rise due to extremely high or extremely low temperature, or differences in production. Or we can simulate a policy like market liberalization, or the opposite trend that is working now, locking the markets, rush of China. Okay, or we can simulate the disruptions to supply chains that we experienced during the COVID. Okay, so adjustment work to the shocks works through changes in prices and wages, operating smoothly in commodity and factor markets. As I already showed, those models are nonlinear because of these constant elasticity of substitution functions, and they are designed to consider adjustment to shocks that work through market mechanisms. Shocks to one market leak to the rest of the economy due to prices and factor flows. Now, what are the outputs? Okay. Basically, what we have is the new equilibrium that reflects the economy after the shock. What is the new equilibrium? What do we have there? We have the estimation of overall income gains or losses from the shock. We can detect the sources of income gain, whether it's sectoral for specific sector, such as agriculture or electricity or other specific sectors, and also whether it's by policy instrument like market access or domestic support. We can also identify and evaluate winners or losses or losers at the country level. And most importantly, we can track the changes in pattern and volume of trade and the income. And eventually, we must understand what is the story that explains how inputs and model combine to determine the outcome, okay? The outcomes that we receive because of the vast nature of the model and a lot of things that are going on, we need to understand what was the most important shock that was driving the change. So in order to trace the differences in the results, we should understand that those models are, the results are deterministic. Okay, the outcomes are completely determined by choice of inputs and the models. There are no residuals in this analysis. And differences in simulation results are basically driven by differences in choice of inputs and model and or the closure rules of the model. Now, the story must explain why the choice of inputs and model is appropriate or optimal for the question of interest. So now, after we finish the general description, okay, let's go to what we are doing here in Awesome. So our team focuses on water, as I said, in the weapon axis at the macroeconomic scale. So as we see, the increase in natural water scarcity is driven by increase by population or decline in the supply of natural waters because of climate change or bad management. And from here, we can see that scarcity of water can affect food and ecosystems, and from there, all economic activities in a given region, and from there go to other regions as well. Okay. So here we analyze what is the role of alternative water sources in the mitigation of the impact or in the adaptation to climate change. But alternative water sources, whether desalination or treated water, also have waste, brine from desalination and greenhouse gas emissions due to the energy that is used for their supply, for their provision. So, and this impact is, as we see, is not only economy-wide, it is also transferred to the international, through the international trade to, in our case, Mediterranean, but also Mediterranean countries are not isolated from the rest of the world. So we take into account in our analysis all the economic activities of the entire economy, world economy. Now, our challenge is to create a projection of what will be, okay, due to climate change in, let's say, 30 years from now. So the way we work in computable general equilibrium to analyze the impact of the shocks, not now, but in some time in the future, we basically start with the actual state of the economy from the database, from the years that the actual data is available in the social accounting matrix of the model. For GTAP, it's 2014. Then we create the future state of the economy according to projections of population growth and of skilled and unskilled, share of skilled and unskilled labor, and how much land will be available for use, and what will be the pace of technological progress to analyze what the economy can look like. Okay, so this is the projected state of the economy, let's say in RCP2. Here, to create this future state, we used the data from our partners from the Greek team of Work Package 2 to create this future state. Okay. Then we say, okay, but there will be climate change impact on land productivity, on availability of land and water, other impacts that we consider. So basically, we see a difference between the equilibrium with climate change comparing to the initial one. Okay. But in our project, we have other moderating, let's say, impacts, which are desalination and use of reused water, of treated water, and also aquaponics, basically allows to provide food with less use of water and land. Okay, so our role is to quantitatively estimate what would be the role of alternative water sources and also of precise agriculture in adapting to climate change in this sense. But the challenge is the data, okay? As I described before, we need a very detailed data in monetary terms for all sectors and all world regions, okay? So this is our challenge, how we, within OSAM, where we are the only group that focuses on macro scale, can both collaborate with the partners that work on regional scale and yet employ the results of their analysis, of your analysis, in order to have to build from this collaboration and to have meaningful results evaluation. However, I must say that there are different possibilities of collaboration, and this is something that I would like to dedicate. Do I have a few more minutes to continue, or would you like me to stop here, Elena?
Yes, please, you can go on, Ruslana, thank you.
Okay. Now, after I described how great this model is, I must say that because the model is general and global and depicts and represents macroeconomic closure, okay, macroeconomic balances drilled on microeconomic theoretical basis. It is a top-down model. Yeah, it has a vision from above on the economy, and it is very detailed on the coverage, the broad coverage of its sphere. But it cannot compete with model that is sector specific or technology specific. We call it bottom-up model, okay? On the details in the representation of a specific sector or specific technology. And here we can talk about the representation of biodiversity or ecosystem services, or representation of agriculture or water management, and precise agriculture. Okay, so the strengths of CGE is the interlink between sectors. The weakness is that each and every sector is depicted with some simplifying assumptions. Okay, therefore, when we can collaborate with different models, it basically allows for bottom-up models to have the broader view, the interlinks that CGE allows for, and for our top-down modeling exercise to be more specific or accurate on the results for sector-specific and technology-specific analysis. Okay. The way this collaboration can work is generally defined or for soft or hard linking between different models. So I talk here on linking between general equilibrium and partial equilibrium models. By partial equilibrium, I mean any bottom-up model, any of models that you guys employ. Okay. So basically, communication between the models can be done in various stages. We can work on one-way linkage between the bottom-up model, where the results from bottom-up model go to CGE, and CGE then analyzes the results using the results from the bottom-up model as external shocks, for instance. This is something that we are considering doing with the results from the what needs model, right? What David supplied us is basically in the results of the projected use of food according to different scenarios, so we can track how the consumption changes due to climate change, and then pose it as an external shock to our model. The link can be the other way around. Yeah, from results of CGE model, we can go and feed them into a detailed top-down model, which is basically what was the idea in collaboration with the energy model in work package 2. Yet there may be a two-way linkage. Okay, so both of models feed in. Okay, transfer. So there is kind of a loop in the analysis when results from one model are fed into the other model. The other model is calibrated or is calculating the new equilibrium, and then the new equilibrium results are fed back to the original model. So, and this loop should go until the results converge. Okay. Or there can be a sequential calibration of multiple parameters between the models. So there is each of those possibilities has advantages and disadvantages. And of course, a two-way linkage looks more productive or more accurate, but sometimes the models do not speak the same language, so we cannot simply iterate between them. Sometimes the computation is so time-consuming or not really possible, so the added value of the consecutive iteration is not beneficial. Okay, is not cost-effective into introducing this effort. So this is something that we need to consider for the future. Okay. So the way that we can exchange data, okay, I said that basically for CGE we need monetary values, but the model can also incorporate the percentage change, okay, in quantity or percentage change in productivity or percentage change in costs, such as what we are doing with what needs and plan to do with energy and plan to do or are in the process of doing with aquaponics. Okay, so specifically for welfare analysis, the link that we still didn't establish in this project is with ecosystems, and this is something that I think it's worth the effort, if not for this specific project, then at least for some future projects and proposals. So in general, I see vast potential for collaboration. And here I stop and ask you what do you think? Lenia?
Thank you, Ruslana. Thank you for the great talk and for your insights of the CGE model. So here I open the floor for questions. If there is any question as written by Ilenia in the chat, so please put your question in the chat, and then I will propose them to Ruslana. Maybe I can just start with a quite general but important question, like what do you think is the biggest challenge for a fresh researcher working with a CGE model when you have to set up the model? What is the biggest challenge and what is your recommendation for the setup and the first approach in the CGE modeling? Thank you.
Well, as a fresh researcher, not so far ago, I must say that the researcher should be ready to spend a lot of time to learn, because this type of analysis requires understanding the microeconomics, the macroeconomics in theory, then understanding the modeling framework, okay, how, the programs that run it, how the equations are specified, and then working on the data. And all of this is before you run your first analysis. So it is so the initial work is time consuming, but once you master it, then it goes much faster and easier.
Thank you.
Elena, there's a question in the chat. If you want, I can read it out loud directly. So perfect. Okay, so I mean, it's for Ruslana, obviously. One question about the use of scenarios. How can a CGE handle the uncertainties with respect to future projections? You showed how you can modify the economic analysis for a given scenario, but how can you extend it to a set of possible futures? Thank you.
Okay, this is a great question. Basically, CGE does not explicitly incorporate uncertainty. We can have several different scenarios, right? And then we can compare the resulting equilibrium between each of the scenarios. So this way, we try to cope with the fact that things are unknown and can change in different ways. So it's comparative static between analysis between different scenarios. The larger the envelope of your scenarios, the broader is the coverage of possibilities that you take, but it comes at the cost of computational time, and you need to balance between how broad the results that you would like to cover and how much time you must invest for incorporating the shocks of each of the scenarios. Sometimes the scenarios also must involve changes in the baseline or changes in some sectors, which is very, again, time consuming.
Okay, thank you. And there are also other questions arriving, so we can keep this mode, so I keep reading them to you, if that's okay. So the second one is there any data for different types of water? What if there is no data for it in a particular region? And second, a second question would be, how market closure decisions would impact the final results. If you want, I can read also the third question and you pack them together. What do you think, Ruslana? Cool. I mean, then there's a compliment by Phoebe, who says that Ruslana is a wonderful teacher and adds that one major challenge is how to incorporate systems approach and uncertainty. So just building up on what you said. And then another question. Could you explain briefly why CGE models are often preferred in this field? I guess climate impacts and climate policy field. Also, with respect to the SGE models or agent-based computational economic models. Okay.
Okay, I'll take it for
and
now.
Then,
yeah. Okay.
Can I add another one? Okay.
Maybe it's enough. No.
just the last one, and then okay. Perfect. Okay, so is there any metrics to evaluate or judge the performance of one CGE model based on its difference between the simulated and observed economic components? Okay, so I guess that you have
between simulated and actual. What is the comparison between simulated and
simulated and the observed economic components? Yeah, I guess actual. Okay, so I think you have plenty of material for the Q&A.
So basically, about I think Phoebe's comment on the system approach for the uncertainty, I think that this is the strength of this project where we have both in work package 2 and in work package 3 models that explicitly deal with uncertainty. So we count on our collaboration with FIM model, and I don't think it will be a direct link. It is feasible, but maybe we will need 3 or more awesome projects to create a direct link between the models. But our goal is to start with Sergio and Marta from the same baseline, start with the same initial structure of the economy, and then impose same kinds of shocks, and so that we will have this large envelope of results coming from general equilibrium model and from the IAM. Each of them can have different strengths and different scope of analysis and results. And I think that this will definitely be for the benefit of this project and of the accuracy of our projections, or so-called. Now, about the data for different types of water. Okay. This is something that we struggle on now. Our partners know that we collect and impose this data for quite some time now. And Orna and Yula do a terrific job with tracking the data on water divided for natural water sources, desalination and treated water on each and every country in the world. Some of them don't have desalination. Some of them have different shares of desalination and treated water. So this information is something in the starting point that we must have. Then we must have the data on who uses each of those types of water. This only whether the desalination goes only to households, or it also goes to the agriculture. Whether only industrial users use treated water or other sectors too. So who uses each of the types of water? And most importantly, and this is where the data is also scarce, is what is the production function and what are the expenses? How those different water types differ for costs, okay? This is the most challenging in our sphere because we must know in order to say how the economy will react, what will be the change in the relative prices that I talked before. we need to know the initial price that is driven from the costs of production of each and every type of water in each and every region in our global model, okay? And this is our challenge. So we hope that we will be able to find as much data as possible, and where the data is not available, we will build on our Israel experience. In this sphere, Israel is about 1/3 of the total water supply in Israel comes from desalination, and from about 70 to 80% of water is treated for tertiary or secondary treatment. And from our the knowledge that we gained in the Israeli model, general equilibrium model with water, we can learn about those production functions. Of course, it doesn't mean that in every other region the production is characterized by the same characteristics as in Israel, but this is where we will not be able to find the data. This is probably the assumption that we will make. Okay. Now, how the closure impacts the results? It can impact quite significantly. By closure, we mean whether the economy is traded in real terms, whether the exchange rate is fixed, what we assume about inflation, what we assume about the flow of labor between different regions. Each of those parameters, or keeping them flexible or strict, presents the result in different terms. And the modeler should be aware that fixing one thing, fixing prices will affect something on quantities. Fixing labor, maybe due to closures, lockdowns, will affect the results of the economy. So, as I said before, the way that we decide on the closure will impact the results. And this should be part of the story that we then use to explain why we got A and not B and not C. Okay. Then I was asked why the CGE models are so popular versus agent-based models or other models. Well, there is a fashion for everything, but you know, as I said, people acknowledge the strengths of the model, where we don't live in an isolated world. Everything is connected, and CGE can represent quite accurately this connectivity. But CGE is not applicable for many other analyses, so we should use them where it can have a significant result. But another point is there is an effort to combine, to link in different ways between the different models, as I explained, to capitalize on the strengths of different models. So there are modeling exercises where there is a significant, an explicit link between CGE and agent-based models. There are exercises where there is an explicit link between agricultural or energy models and the CGE. And so in order to gain from the characteristics of each of the models and to have more accurate representation. This is the idea. And the final one, what was matrix? Something about the matrix?
Okay, so let me read it again. Yes. Is there any metrics to evaluate or judge the performance of one CGE model based on its difference between the simulated and observed economic components?
Well, yeah. So the validation of results, if this is what this question is about, is quite complicated in CGE models, because we say we start from the initial equilibrium, then we simulate one single shock, and we compare the starting point with the new equilibrium. Okay, but in reality, nothing is fixed. A part of the simulated shocks, in the meantime, there are many other things going on. The population change, the tastes change, the technology change. There is a technological progress. There are new technologies developed. There is a structural change between different sectors. People move from working in one sector to another. So many things do change in between that we didn't model. So even though this is a comprehensive model, overall inclusive, etc., the reality is far more complicated. Therefore, validation efforts are quite scarce, but there are validation efforts. I know some papers that tried to pick the major shocks to the economy, introduce them to the model, and say, let's say we had the starting point of the year 2010, and then we know the new equilibrium, the actual data for 2018, and in the meantime we had specific key shocks to the economy, I don't know, because of the subprime crisis or other major shocks. They impose them to the model and usually do reach the new equilibrium that is projected by the model. It is quite close to the actual data of the responsible or of the respectful year. Okay, so this is between the actual data and the projection of a model. How projections of different models, how they accurate, this is usually done not between different CGEs, but for instance, for CGE with a link to a specific bottom-up model or without, or with this type of parameter or with other parameter, or with a more detailed representation of energy sector or without. Okay, so these are the validation exercises that are usually, their goal is to show that the effort in the modeling effort and the effort in collecting the data, like what we do now with water, yeah, was worthwhile, so that the results of the updated model are more accurate than the version that was before.
Okay, perfect. Thank you, Ruslana. So since we have a couple of minutes, Phoebe wanted to come in and make a comment. So I'm enabling her.
Basically, hello, Ruslana. I just wanted to say what an amazing teacher Ruslana is. These are very complicated models, and she presented them in such a clear way. Thank you, Ruslana, for this. Also, I think as awesome, but also beyond awesome, we can definitely think of the cutting edge issues that are now populating the literature. Can we have a systems approach that is, can we merge into this more systems, given that there are models for other systems outside the water, food, energy nexus, and have a systemic approach to this analysis. I know that general equilibrium models are very good in that, But I think we can make it explicit in terms of, you know, writing a paper of how general equilibrium models can address this systems approach. And then it is a matter of things of how you deal with uncertainty and how much uncertainty you allow in your models, which are very cutting edge issues, and what kind of scenario generation processes do you engage in order to integrate in the general equilibrium system. And the last one, I was wondering, although I know it's going to be a challenge, how can we introduce stakeholders projections or perceptions into these models? I know that they have to be not very flexible in order to really manage all these equations, but maybe it could be we can attempt to start thinking around introducing a behavioral element beyond the one that exists there, which is obviously in the demand curves, but you know, a behavioral element that will allow some changes in the structural equations. But thank you so much, Ruslana. Thank you so much for this.
Okay, so Phoebe asked how we can incorporate in the model stakeholders' projections or beliefs or some behavioral elements. I think some of them can be incorporated quite easily if, well, as I said, this general equilibrium reflects the market reacts to changes in prices. Okay, but there are some there may be some stringency that even if prices of some sources are cheaper, but people just don't believe that or don't want to use them. Okay, I mean, I don't know, some perceptions about desalination or about treated water or about any other kind of natural or not natural resources that for some maybe geopolitical reasons or other beliefs cannot be used even if they are cost effective. And then we can just limit the use of those sources. And this is something that can be directly analyzed within the model. But anyhow, not everything is modeled can be easily modeled, but we can discuss and definitely what things we can directly incorporate. Okay, some other comments in the meantime?
Perfect, thanks, Ruslana. Ilenia, do you have any other questions? Maybe one last one, and then we close.
Yes, there's one last question. Okay, so it's. I would like to ask if the CGE model is capable of generating any type of scenarios for water use or land use for the future, or are these required as inputs? Especially for water resources, available data are quite limited, especially in regions like Nile River Basin.
So again, if you understand the question is what should be the water use and land use. So that we project what is the amount.
Exactly. So if the model is capable of generating scenarios for water use or land use in the future, or if water and land use are required as inputs. And then the concern of data availability for water resources in certain regions.
Yeah, so this is a question basically of what we decide is exogenous and what we decide was endogenous, okay? we can say that we can simulate with the model, let's say, due to growth in population, due to changes in food taste, or I don't know, some changes. What will be the requirement of water? Okay, so then water requirement is the output of the analysis. Okay, actually, this is what we are going to do here when we simulate climate change. Basically, for our baseline scenarios, we analyze the use of natural waters, and then we say, due to climate change, the reduction in precipitation and the evapotranspiration will lead to, let's say, reduction in 10%. This is something that we will take from exogenous as an exogenous shock. Okay, and then we say, if we don't have desalination, this major shortage will create a negative effect on the economy. But with desalination and with the reuse of water, we have a kind of supplementary supply of the water sources, which can then buffer and reduce the losses. So we do have different types of projections, and then we play and compare between them.
Okay, perfect. And there aren't more questions, so if you agree, we can close with 5 minutes in advance.
Perfect. So it is okay. Yeah, we are quite on time. So thank you again, Ruslana, for the great talk and training on the CGE and for the discussion. So as mentioned, the recording will be available soon. And with this, I say, if there are no other comments from the panelists and organizers, then we can close the webinar here.
Thank you.
Have a nice day.
Thank you. Bye-bye.